Okay, we said our domain of R is 1, 3 because 1 and 3 and range is Y and Z. So as a second example to give some idea, set inclusion subset is a relation, right? We mentioned that on any collection of sets, for given any pair of sets, A and B, either A is subset of B or A is not subset of B. Right? And third one, a familiar relation on the set Z of integers is m divides n and a common notation for this relation is to write m divide n when m divides n and d as an example. Next, okay, take page 3 and start page 4 as an example 4. And let's say the set L of lines in the plane perpendicularity written in that symbol. This is the means of perpendicular. Is a relation on L so that is given any pairs A and B either A perpendicular to B, or we can say A is not perpendicular to B in that symbol. Similarly, we can add as a more relation is parallel to symbol like that, parallel to line is a relation again on L, since either A parallel to B or A is not parallel to B. So we saw some definition as a perpendicular or parallel. Okay, next one. Next one. Salona gidin. Tamam, salona. Arada başka bir yer. Zeynep'i senin odana getirsin. Bilgisayarı taşısın. As a 5, and let A be any set an important relation on A is that of equality. So A pair, which is inside of that relation, A should be member of set A, which is of course denoted by equal symbol. The relation, but there is something is different, is called the identity or diagonal relation on A. And it is also denoted by delta A, or just delta. I'm sorry, delta, not A. And last one is giving some, relation properties. Again, there is the set A, and there is a product A and empty. Okay, make it empty set symbol. Are subset, of course, of A cross A or A product A. A called the universal relation. A product A is a universal relation, an empty relation, respectively. So we saw some relation as a product at the beginning of relation chapter, and we saw as a perpendicular relation, as a subset relation, is subset or not subset, perpendicular or not perpendicular, and so on. And there is also inverse relation. There is something is reverse, and that part is the inverse relation. Okay, we know as a R any relation. Of course, there is the tool set for that relation, like A and B. So that relation is, from set A to set B. The inverse of R, for that relation, denoted by R to power minus 1. This is going to be inverse relation. It means relation from B to A. So R inverse is equal like BA pair, which means AB pair is belong to relation R or member relation R. As an example for that condition, okay, let's try the example. We have set, A, and inside of the set we have as a 1, 2, 3. This is our, basic element in set A, and there is the set B. We have, okay, let's write the example from your book, X, Y, Z, X, Y, Z. So let's write the relation as a R. Okay, R relation already given. Pairs like 1 to Y and 1 to Z. and 3 to y. So what is the inverse relation? What is the inverse relation? Okay, find r powered minus 1. We are looking for that one. Of course, reverse of that pairs, right? As a what? 1 to y. My voice is okay, dear friend, and can you hear me? Y to 1. Okay, these are very simple, alright? Y to 1, Z to 1, and Y to 3 as the inverse relation for that R. So, we saw the sum set theorem, as you remember, as a list form of the set, and there is the Venn diagram of the set, and we saw some relations as a like list form when you consider the set theorem. So we can represent that relation some different way also. Let's see how we can represent that relation in our new page as a page 5 as a pictorial representatives of relations or representation of relations. Okay, pictorial representative of relations. So also that pictorial form will help us to understand uh, other our features theorem like graph theory and something else like that. So we can show as a relation, for example, r square r product r and there is the pair x y and relation like the set E and x squared plus y squared is equal to 25. This is give us, okay, let's write as an example. This is give us as a circle as a x and y plane. In that relation, like y and x. So draw as a exact circle is really hard. Okay, let's try my best. Okay, let's say here is 5 and 5 and 5 and 5. This is the minus 5, of course, and here is minus 5. This is x squared plus y squared is equal to 25 is a circle. And also, for example, we have as a set A, and in that set 1 2, 3, and 4, there is the, A square relation from A to A as a relation set, as a pair like 1 to 2 and 2 to 2 and 2, 4 and 3 to 2. So I need some more place. 3, 4 and 4, 1 and 4, 3. So if I want to draw uh, that relation as a pictorial, so I need the 1. So I have 1 and I need 2, 3, all member of the set A, and 4. You can make it different, place in the space of that member, but I draw like that, or I point to member like that to make the relation, in small place. Okay, first relation 1 to 2. Okay, this is the relation arrow 1 to 2, directed as a from 1 to 2, and 2 to 2 as a, this is the relation as a pictorial form, 2 to 2 and 2, 4, and here is also one relation from 2 to 4 and 3 to 2 and 3, 4. Okay, and 4, 1, 4, 1 and 4, 3. Okay, I can draw like that. If you change the place of that, you know a set member, of course you will have some different shape, but and exactly you have to, draw the relation like that. Okay, uh, we can represent relation also some different form. Let's directly use some example to explain that relation. It is gonna be easy to write whole, theoretical explanation. And let's say we have as a set A, let's say we have in member of that set as a 1, 2, 3, and there is the set B, X, Y, and Z. So let's write or define the relation as a R as a 1 to Y and 1 to Z and 3 to Y. Is it the previous example? So I define the relation like that. Okay, first one, and write our relation on matrix form. form, and B uh, as a, you know, Venn diagram and arrow representation relation. So first one is really easy. I can use, you know, row as a member of A, like 1, 2, and 3 as a case A, matrix form. Let's say we have here as a B member X, Y, and Z. So row is, you know, my domain, right? I defined before for the relation, and column are my range. So 1 to Y, 1 to Y, I have relation. I will put here as a 1. 1 to Z, I have relation. I will put here 1. And 3 to Y, I have relation here 1. Rest of the, 1 to X, there is no relation. 2 to X, there is no relation. And 2 to Y, there is no relation. And 2 to Z, there is also no relation. And 3 to X, no relation. And 3 to Z, there is no relation. For case B, I have, set A, the Venn diagram, and set B. And set A, I have 1, 2, and 3, X, Y, and Z. For that relation, I'm gonna use, arrow representation from 1 to Y, 1 to Y, and 1 to Z, and 3 to Y as a last. So this is my uh, pictorial representation. This is the matrix of relation, and this is the, Venn diagram and arrow, representation or arrow diagram as a solution. Any question for that representation? Buket? Okay, next page, composition of relation. Now, we saw relation from set to set. We defined some, relation like product, subset, less than, greater than, and there is, mathematical form for the relation like the xy, and there is the, relation a to a. This is the relation from a to a and pictorial form. And now we will talk about some composition of relation. Now we will combine more than one relation, and we define that thing as a composition relation with the new page, the page 6, and composition of relations. So we have as a tree set A, B, and C. Now we have tree set A, B, and C. and there is, you know, relation on R relation set. So that relation from A to B, and there is also second set as a S. In that set relation, in that set we have relation from B to C. Okay, let's draw as a pictorial form. We have set A, set B, and set C. We have relation from, okay, make it something like that. So this is the R, and we have something like relation from B to C as a S. So we don't have any detail, just we mentioned something like that. So you can say R is, of course, subset A product B, and S is subset, let's say, B product C, and then according to that explanation, then R and S give rise to a relation from A to C, right? Because I'm starting set A coming from to set B relation R, and S is carrying my relation from set B to C. So finally I will come with that relations as a S and R from A to C. So I will denote that by R composition S, and defined by R composition S. If I have A to C relation, A inside of the set A, C inside of the set C, if for some B is the member of set B, and we have, so I'm sure you will get the meaning of that one, A relation to B as a relation R, and I have B relation to C with the S. So I will say as a R relation composition with the S, which is there is the AC pair in that composition. There exists B member of B for which AB is member of relation R, and BC member of relation of S. So this is the composition relation. I have two relation between that, three sets. Relation R is here and relation S here. And according to that relation, I define the composition relation from R using the R and S relations. So let's write example. So I have a set A 1, 2, 3, and 4, and there is the set B A, B, C, D, and there is a set C X, Y, and Z. So I have relation from A to B. There is the pair like 1A and 2D and 3A, GB, and 3D. If I want to write whole product A and B, what is going to be total member of that relation? Okay, this is a question for you. And there is a set B to C relation as a S, and pair BX. Okay, who is going to answer that? 16, yeah, exactly. So it means R is the subset of A product B, right? And BX, BZ, CY, and DZ. So I have two relation pairs set R and S. So what is the uh, B product C total member? Here is the 16 and here is the 12, right? Thank you, Buket and Emre. And so what is the relation of, okay, case A, what is the relation of composition R to S? So this is my question as a list form, and B is going to be, arrow diagrams. Okay, what do you think? One goes to A goes to somewhere else in relation set S? No. 2 goes to D, D goes to Z. Okay, 2 and Z. 2 and Z. Is that clear? One goes to A, but A not inside of to that pairs as a first element, and I'm looking the second pair in relation R. 2 goes to D. I'm looking for D as a first member of that pair. Okay, I'm looking here, and there is DZ, It means 2 goes to Z as a composition of relation R to S to Z. Now 3A, I'm looking for A, there is no A, so I pass that one also. 3B, I have B, right? 2B, it means I can go 3B, B to X, 3X, and 3B, B to Z. It means 3 to Z. Anymore 3D, 3D. Yes, Emre, exactly. I have something as a more here, right? 3D, DZ. It means 3Z. But when I looked here as a composition relation R to S, there is two, yeah, I don't need to write 2 times 3Z. I will write instead of that as a 2Z and 3X and 3Z. So this is my answer. And also I can draw that composition relation as a Venn diagram using the Venn diagram of the set A, B, and C plus 1. I have 1, 2, 3, and 4, and A, B, C, D, X, Y, and Z. Now 1 goes to A, 2, D, and 3A, and 3B, and 3D. So these are the relation of R, and relation S, B to X, B to Z, C goes to Y, D to Z. So D is the relation as a S. So we show as a relation, R to S as a composition relation, and we represent here as a arrow diagrams, and we can do that things using the matrix form, right? How we can do that solution? Okay, we know as a relation, we know the relation. Let's write as a C from A to B. So what I have as a B member, A, B, C, and D. So this is the relation matrix of R. This is the relation matrix of R. 1 to, I have 1 to A relation is a 1, but there is no 1 to B, right? 0, 1 to C, 0, 1 to D as a 0. And let's look at the matrix form also, Emre. There is 2 to D, right? I have here and rest is zeros, and 3 as a, B, and D. Here is the zeros, and there is no 4. And relation matrix for S. Now I have here as a, B, C, D as a row, and X, Y, Z as a column. Right? There is no A, 0, 0, 0. For B, and B goes to Z, and also B goes to X, 1, 0, 1. And C goes to Y, and 0, 0. And C goes to Y, and D goes to Z as a 1, 0, 0. Now, if I want to write as a multiplication, MR as a matrix R and matrix S. So this is the M is equal RS. This is going to be is equal 1, 2, 3, 4, and column X, Y, and Z. X, Y, and Z. Here is gonna be 0, 0, 0, 0, 0, 1, 1, 0, 2, and 0, 0, 0. So do you think that this is correct? 0 times 1, 1 times 0, 0 times 0, 0 times 0 is going to be 0. 0 times 1, 0 times 0, 1 times 0, 0 times 0, and 0. 0 times 1, 1 times 0, 0 times 0, 1 times 0. First row is going to be 0, and second row 0, 0, 0, and 0, and 0, 0, 1, 0, and 0, and last member of that multiplication 0 times 0, 1 times 0, 0, 0 times 0, 1 times 1 is 1, and third row 0, 1, I have 1 here, and 0, and 0, and 0, 0, 1, 0, and 0, and last column to third row of MR, and 0, 1, 0, 1, 1 plus 1, 2, and last row totally 0. It means here is going to be last row is going to be 0. So this is the multiplication of matrix R to matrix S. If I want to write matrix R relation composition with the S, this is going to be is equal 1, 2, 3 as a 4, X, Y, and Z. That 2 is going to be 1 because of that condition, that situation. And 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0. This is the matrix of composition relation. Because of that one, 2 goes to Z, 2 goes to Z, 3 goes to X, 3 goes to X, 3 goes to Z, 3 goes to Z as a 1 times 0. Multiplication you can see as a 2, but composition of relations, you will see that matrix. And now new title, but we can continue that one as a next lecture. I offered the department as an extra 2 hours for weekdays, but they didn't put any extra hours on Tuesday. I checked your schedule, weekly schedule for the lecture. There's no, any lecture on Tuesday, but I don't know. No, I won't give you any quiz. Just I will send you some free study question. Please solve that question before the midterm. Okay. End of the chapter I will write as a homework, but I won't evaluate that homework. Just solve that's the question. It is gonna be helpful for you to understand what is inside of the chapters, what is the important for you, for example. And what else? I will continue for next lecture as a type of relation, types of relations. So we will classify the relations according to some, properties. Then we will continue with that, classification of the relations. I offered the, 9 to 11 for not Tuesday, Thursday, but they didn't accept it as an extra 2 hours to cover something, maybe chapter 2 we will cover some, more theoretical part, and also we can solve some, extra example as a, study example. End of the chapter. You have data structure 9 to 11. Okay, they didn't answer my, email. They didn't reply me anything. If they offer different 2 hours, I will accept it. So any question? We covered the half of the chapter 2, and next lecture we will talk about the types of relations. We will start that part, and then maybe next lecture we will complete the chapter 2. Then we will start chapter 3 as a function of algorithms. So these are really basic. I'm sure you know that, set theorem and relations theorem from your, math course, maybe from high school. And your book also, giving really details, and there is so much example to understand the idea. And also you can follow the recorded lecture. Okay, any question? Okay, thank you for all coming to my lecture. I'm sorry for disconnection of our lecture. It takes some times. I wish you all have a good weekend. Okay, thank you, Hilmi, Ekin, Buket, Anil. Thank you for all, and see you next lecture. Okay, take care, dear friend. Good day. See you.